Hi there, and a heartfelt welcome. I'm so happy you've joined me today. Before we dive in, I'd love it if you could share in the comments where in the world you're tuning in from and what time it happens to be for you right now. It's always so special to see our little community connecting across time zones. A gentle thank you as well to everyone who has already subscribed and shown love with likes on the videos. It truly makes a difference. And if you have ideas or topics you'd like me to cover, please let me know in the comments. With that, let's get started. Chapter 1. Understanding Quantum Mechanics Basics. Imagine a world where the rules that govern reality seem to bend and twist. A realm where certainty fades into the background, replaced by a landscape of possibility and intrigue. This is the world of quantum mechanics, a branch of physics that delves into the very fabric of the universe, revealing the mysterious behaviors of particles at the smallest scales. As we step into this fascinating domain, we find ourselves on a journey that challenges our perceptions and ignites our curiosity. At its core, quantum mechanics invites us to embrace principles that defy our everyday experiences. One of the most captivating ideas is superposition, which suggests that particles can exist in multiple states at once until they are observed. Picture a spinning coin suspended in the air. It is neither heads nor tails, but something in between, a blend of both possibilities. This concept challenges our classical understanding of reality, where objects are expected to be in one specific state at a time. In the quantum realm, however, the act of measurement plays a crucial role, collapsing these multiple possibilities into one observable reality. As we explore further, we encounter another cornerstone of quantum mechanics, uncertainty. This principle, famously articulated by Werner Heisenberg, tells us that we cannot precisely know both the position and momentum of a particle at the same time. Imagine trying to catch a fleeting shadow in the fading light of dusk. The more you focus on its exact location, the more elusive it becomes. In the quantum world, this uncertainty is not merely a limitation of our measurement tools, but a fundamental characteristic of nature itself. It compels us to rethink how we understand certainty and knowledge, urging us to embrace the complexities and unknowns that lie beneath the surface. The journey from classical to quantum physics is a tale of evolving thought, marked by extraordinary discoveries and revolutionary ideas. In the early days of physics, the universe was viewed through the lens of classical mechanics, where Newton's laws provided a framework for understanding motion and gravity. However, as scientists delved deeper into the microscopic world, they began to encounter phenomena that could not be explained by classical theories. The very existence of light as both a wave and a particle challenged the traditional boundaries of physics, leading to a paradigm shift that paved the way for quantum mechanics. Key experiments played an instrumental role in shaping this new understanding. One of the most significant was the double-slit experiment, which elegantly demonstrated the wave-particle duality of light and matter. When light is shown through two closely spaced slits, it creates an interference pattern on a screen, suggesting that the light behaves as a wave. Yet, when individual photons are sent through the slits one at a time, they still produce the same interference pattern, implying that each photon somehow passes through both slits simultaneously. This experiment raises profound questions. How can a single particle exhibit wave-like behavior? What does it mean for our understanding of reality? Another groundbreaking experiment was the photoelectric effect, which Albert Einstein famously explained. By shining light on a metal surface, electrons are emitted, providing evidence that light can behave as a particle or photon with quantized energy. This realization not only earned Einstein a Nobel Prize, but also led to the development of quantum theory, fundamentally altering our perception of light and energy. It prompts us to ponder, what other hidden mysteries lie within the fabric of our universe, waiting to be uncovered? Throughout history, outstanding individuals have contributed to the evolution of quantum mechanics, each adding their unique perspective to this complex tapestry. Figures like Niels Bohr, whose model of the atom introduced the concept of quantized energy levels, and Richard Feynman, who brought clarity to quantum electrodynamics, have helped shape our understanding of the quantum realm. Feynman once said, "The thing that really interests me is whether God had any choice in the creation of the world." This question reflects the profound depth of inquiry that quantum mechanics inspires, inviting us to consider the nature of existence itself. As we immerse ourselves in the principles of quantum mechanics, it is essential to recognize the implications these ideas have on our understanding of reality. The notion of superposition and uncertainty encourages us to embrace the unpredictability of life, reminding us that not everything is as it seems. It is a call to be open to the mysteries that lie ahead, to explore the unknown with a sense of wonder and curiosity. Imagine standing at the edge of a vast ocean, the waves lapping gently at your feet. Each wave represents a possibility, a potential outcome of a quantum event, waiting to be realized. As you gaze out at the horizon, you begin to understand that the universe is not merely a collection of fixed entities, but a dynamic interplay of energy and information. It is this interplay that fuels the heartbeat of existence, inviting us to participate in the dance of life with all its uncertainties. In the chapters to come, we will delve deeper into the intricacies of quantum mechanics, exploring its applications and the profound questions it raises about the nature of reality. We will uncover how these principles have not only shaped our understanding of the universe, but have also influenced technology, philosophy, and even our daily lives. As we embark on this exploration, let us carry with us the wonder and awe that quantum mechanics inspires, embracing the beauty of the unknown and the possibilities it holds. As we stand at the threshold of this new understanding, let us remember that the journey through quantum mechanics is not merely an academic pursuit, but an invitation to expand our consciousness. It challenges us to think beyond the confines of our perceptions, to question our assumptions, and to embrace the marvels that lie within the intricate dance of particles and waves. In doing so, we embark on a path that leads to a deeper appreciation of the universe and our place within it, a journey that is as profound as it is enlightening. As we further explore the foundational concepts of quantum mechanics, we come across remarkable implications that these ideas have on our understanding of reality. One such implication is entanglement, a phenomenon that seems to defy the classical idea of locality, where objects are only influenced by their immediate surroundings. Imagine two particles that, despite being separated by vast distances, remain interconnected in such a way that the state of one particle instantly influences the state of the other. This instantaneous connection, famously described by Einstein as spooky action at a distance, challenges our intuitions about how the universe operates. What does this mean for our understanding of information and connection? As we ponder this question, we can visualize a pair of dancers, moving in synchrony, even when divided by miles of space. Their actions echo each other, creating a bond that transcends the physical barriers that separate them. This entangled state implies that particles can share information instantaneously, leading to profound questions about the nature of communication and the structure of reality itself. The concept of entanglement was brought to light through experiments such as the Bell test experiments, which demonstrated that the predictions of quantum mechanics hold true even against the backdrop of classical physics. These experiments revealed that particles can be entangled in such a way that measuring one particle affects the other, no matter the distance between them. This realization has profound implications for fields such as quantum computing and cryptography, where the potential for secure communication could revolutionize how we share information. Throughout history, the journey of quantum mechanics has also been shaped by influential figures whose curiosity and insights have propelled the field forward. Among them is John Bell, whose work on the foundations of quantum theory led to the development of Bell's theorem. This theorem provided a way to test the predictions of quantum mechanics against those of local hidden variable theories, ultimately favoring the strange predictions of quantum theory. Bell famously stated, There are no hidden variables in quantum mechanics. His assertion serves as a reminder of the complexities that lie within the quantum realm and challenges us to reconsider the very nature of reality. As we navigate this terrain, we can't help but wonder what lies beyond our current understanding of quantum mechanics. The study of quantum mechanics has opened doors to new technologies and philosophical inquiries, extending its influence beyond the realm of physics. Quantum mechanics has laid the groundwork for innovations such as quantum computers, which harness the principles of superposition and entanglement to perform calculations at unimaginable speeds. Imagine a world where problems deemed impossible to solve could be addressed in mere moments, unlocking solutions to complex challenges in medicine, cryptography, and artificial intelligence. Moreover, the philosophical implications of quantum mechanics extend into our understanding of consciousness and the nature of reality. Renowned physicist and philosopher David Bohm suggested that the universe is an unbroken whole, where separateness is an illusion. He posited that everything is interconnected at a deeper level, echoing ideas found in various spiritual traditions. This perspective invites us to reflect on our place in the cosmos and the interconnectedness of all things. As we ponder these connections, we might envision the universe as a vast, intricate web where every strand vibrates with energy and information. Each particle, each wave, contributes to the symphony of existence, reminding us that we are all part of something greater than ourselves. How does this understanding shift our perceptions of individuality and community? The exploration of quantum mechanics does not merely reside in the esoteric realms of science, but resonates deeply within our everyday lives. The principles derived from quantum theory have begun to impact various fields, from medicine to technology, offering new avenues for discovery and innovation. Techniques such as quantum imaging are being developed to enhance medical diagnostics, while quantum cryptography promises to revolutionize data security. It is indeed a thrilling time to engage with these concepts, as the insights gleaned from quantum mechanics continue to inspire both scientific and philosophical discourse. Imagine the future where our understanding of consciousness, reality, and technology is intertwined in ways we have yet to fully comprehend. As we delve deeper into the heart of quantum mechanics, we encounter complex ideas such as quantum tunneling, a phenomenon that allows particles to pass through energy barriers that would be insurmountable in classical physics. Picture a small ball rolling up a hill. In classical terms, it must gather enough energy to reach the top. Otherwise, it will roll back down. Yet, in the quantum realm, this ball can mysteriously appear on the other side of the hill without ever having climbed over it. This remarkable behavior not only challenges our conventional views, but also has practical applications, such as in nuclear fusion, where particles must tunnel through potential barriers to fuse together. Such phenomena compel us to reevaluate our understanding of motion and energy. They invite us to imagine a universe where the impossible is, in fact, within reach, igniting a sense of wonder about the potential that lies hidden in the fabric of reality. In the tapestry of quantum mechanics, each thread, each discovery, serves as a testament to the human spirit's quest for knowledge. As we continue our journey through this captivating field, let us embrace the mysteries that quantum mechanics holds, remaining open to the possibilities that lie beyond our current understanding. By doing so, we can cultivate a deeper appreciation for the universe and the intricate dance of existence that surrounds us, forging a connection to the cosmos that is both profound and inspiring. Chapter 2. Defining quantum entanglement clearly. Imagine a world where two seemingly separate particles share a bond that transcends distance, where the state of one can instantaneously influence the state of another, regardless of the space that separates them. This wondrous phenomenon is known as quantum entanglement, a cornerstone of quantum mechanics that paints a picture of interconnectedness at the most fundamental level of existence. At its essence, quantum entanglement occurs when pairs or groups of particles become intertwined in such a way that the quantum state of one particle cannot be described independently of the state of the others. even when the particles are separated by vast distances. Picture two dice, rolled at the same time, yet instead of obtaining independent results, the outcome of one die directly influences the outcome of the other. If one die lands on a 6, the other will too, regardless of how far apart they are. This peculiar relationship defies our classical intuitions about separateness and locality. So how do particles become entangled? The process begins with interaction. When particles collide or interact in specific ways, they can enter a combined state that encompasses both entities. This entangled state is not merely a sum of their individual states, but an entirely new entity, rich with potential. Consider the example of two electrons, each possessing a spin, a fundamental property that can be thought of as a tiny magnetic moment. If these electrons interact, they can become entangled, resulting in a joint state where the spins are correlated. If one electron is measured and found to have an upspin, the other will instantaneously be determined to have a downspin, illustrating the interconnectedness of their properties, even if they are light years apart. The role of measurement in entanglement introduces an additional layer of complexity. In quantum mechanics, measurement is not a passive observation but an active process that influences the state of the system. When a measurement is performed on one of the entangled particles, the act of measuring causes the entire system to collapse into a specific state. This collapse is instantaneous, creating a change in the state of the other particle, despite the distance separating them. Imagine two friends, each holding a piece of a shared secret. When one decides to reveal their piece of the secret, the other instantly knows the entire secret, irrespective of the miles that lie between them. This instantaneous nature of entanglement has sparked numerous debates and explorations in the scientific community. The distinction between classical and quantum correlations is another crucial aspect of entanglement. In classical physics, correlations can be explained by classical laws and local interactions. For instance, if two coins are flipped simultaneously and they both land on heads, the correlation can be attributed to the randomness of the coin flips. There is no mystery. The coins are independent entities that happen to show the same result. However, in quantum mechanics, entangled particles exhibit correlations that cannot be accounted for by classical means. These are non-local correlations, meaning that the entangled particles do not need to have any classical interaction to influence each other. The implications of quantum entanglement extend far beyond mere curiosity. They challenge our understanding of reality itself. Albert Einstein famously referred to entanglement as spooky action at a distance, expressing skepticism about how two particles could communicate instantaneously without any form of signal traveling between them. This skepticism, however, has gradually been replaced by a growing acceptance of entanglement as a fundamental feature of the universe. Renowned physicist John Bell proposed a theorem that provided a way to test the strange predictions of quantum mechanics against classical intuitions. Bell's theorem suggests that if entangled particles are measured, the correlations observed would violate certain inequalities that are upheld in classical physics. This means that the outcomes of measurements on entangled particles exhibit behaviors that cannot be explained by any classical theory of local hidden variables. Numerous experiments have confirmed Bell's theorem, further solidifying entanglement's place in the fabric of reality. As we contemplate the nature of entanglement, we are confronted with profound questions. What does it mean for a particle to influence another instantaneously over great distances? Does this suggest a deeper level of interconnectedness within the universe, a web of relationships that transcends space and time? The story of quantum entanglement intertwines with the lives of the brilliant minds who have explored its depths. Among them is the physicist Anton Zeilinger, who has conducted groundbreaking experiments demonstrating the reality of entanglement. He once expressed, "What is fascinating about quantum mechanics is that it describes a world that is much richer and more complex than we can ever imagine. This richness invites us to ponder the mysteries that lie at the heart of existence." As we drift further into the world of quantum entanglement, we are beckoned to imagine the possibilities that arise from this interconnectedness. If entangled particles can instantaneously affect each other, what might this mean for the future of technology? Quantum entanglement is not merely a theoretical construct. It underpins the emerging field of quantum computing and quantum cryptography, promising innovations that could revolutionize the way we process information and secure communications. Imagine a future where quantum computers, leveraging the principles of entanglement, perform calculations at speeds unimaginable with classical computers. These machines would operate on numerous entangled qubits, creating a symphony of interactions that could solve complex problems in seconds, reshaping industries from medicine to finance. As we contemplate the implications of entanglement, we are invited to reflect on the nature of reality. Could it be that our understanding of separateness is merely an illusion, a byproduct of our limited perception? The entangled particles challenge us to reconsider our assumptions about independence and individuality, suggesting that at a fundamental level, everything in the universe is interconnected. In this realm of quantum entanglement, the boundaries of science and philosophy blur, inviting us to explore the very essence of existence. The phenomenon beckons us to embrace a vision of an intricate and harmonious universe, where the dance of particles reveals a deeper truth, a truth that is as captivating as it is elusive. As we continue to explore the wonders of quantum mechanics, let us carry with us the spirit of curiosity and wonder. Let us ask the questions that stir our souls and seek the answers that lie hidden within the fabric of reality. How does quantum entanglement reshape our understanding of the universe? What mysteries await us as we delve deeper into this interconnected web of existence? The journey into quantum entanglement unfolds like an intricate story, filled with characters, discoveries, and revelations that challenge our perceptions. As we embrace this journey, we find ourselves standing at the threshold of a new understanding, one that invites us to explore the profound connections that bind us all, even across the vastness of space and time. As we delve further into the phenomenon of quantum entanglement, we must consider the implications of this intricate connection between particles. The relationship established through entanglement challenges not only the fabric of physical interactions, but also our philosophical understanding of reality itself. It poses questions about the nature of existence and the fabric of the universe. How profound can the implications of entangled particles be for our perception of time and space? To answer this, let us reflect on the concept of locality in physics. In classical physics, locality implies that objects are only influenced by their immediate surroundings. Information cannot travel faster than light. Yet, in the realm of entangled particles, this notion falters. When one particle is measured and its state determined, the other particle, regardless of the distance, reflects that change instantaneously. This phenomenon suggests a form of communication that transcends our traditional understanding of distance and time, evoking a sense of wonder about the interconnectedness of all things. Imagine a universe where distances between points are not barriers but mere illusions. This idea evokes the thoughts of physicist David Bohm, who proposed a holistic view of reality. Bohm's theory suggests that the universe is an interconnected whole, where each part contains information about the whole. In this view, entangled particles would not simply respond to each other. They would embody a shared existence, an underlying unity that defies separation. The exploration of quantum entanglement has also paved the way for fascinating applications in technology. One of the most promising fields is quantum cryptography, where entangled particles are utilized to create secure communication channels. The principle of entanglement ensures that any attempt to eavesdrop would disturb the quantum state, alerting the communicating parties to potential interference. This development transforms our approach to security in the digital age, providing a new frontier for safeguarding information in an increasingly interconnected world. As we reflect on these developments, we must also consider the role of measurement in shaping the reality of entangled particles. The act of measurement in quantum mechanics is not merely a formality, it is a catalyst for change. When a measurement is made, it influences the entire system, collapsing the entangled state into a definite outcome. This process raises profound questions about the observer's role in the universe. Are we mere spectators, or do our observations actively shape reality? Think about the implications of this notion. If our measurements influence the state of entangled particles, what does that say about our relationship with the cosmos? It suggests a participatory universe, where each active observation resonates through the fabric of reality, weaving a narrative that connects us to the very essence of existence. In contemplating the distinction between classical and quantum correlations, we uncover a deeper understanding of nature's complexity. Classical correlations are straightforward. They arise from direct interactions or common causes. However, quantum correlations are enigmatic, presenting a reality where the connection between particles is not bound by classical constraints. Renowned physicist Niels Bohr famously remarked, "We must be clear that when it comes to atoms, language can be used only as in poetry." This poetic approach highlights the limitations of our classical language in expressing the intricacies of quantum phenomena. The beauty of quantum entanglement lies in its defiance of conventional logic, inviting us to adopt new perspectives and embrace the mystery of existence. As we ponder the nature of entanglement, we are reminded of its profound implications for our understanding of reality. Does the entangled nature of particles hint at a deeper, shared consciousness within the universe? Are we, like entangled particles, interconnected in ways we have yet to comprehend? The exploration of quantum entanglement is not merely an academic pursuit. It is a journey that invites us to reflect on our place in the cosmos. It encourages us to consider the profound connections that bind us to one another and to the universe itself. In a world that often feels fragmented, the realization that we are part of an intricate web of relationships can be both calming and invigorating. As we continue to investigate the wonders of entanglement, we find ourselves at the nexus of science and philosophy, where the boundaries blur and questions abound. What does it mean to be entangled? How does this interconnectedness influence our daily lives and our understanding of the universe? In this moment of contemplation, we stand before the vastness of possibility, ready to embrace the unknown. The journey into quantum entanglement unfolds like a grand narrative, filled with discoveries that challenge our perceptions and illuminate the beauty of existence. The interplay of particles, the role of measurement, and the distinction between classical and quantum correlations all weave together to form a rich tapestry of understanding that beckons us to explore further. As we progress, let us carry the spirit of inquiry with us, inviting curiosity to guide our exploration. The depths of quantum entanglement hold mysteries yet to be unveiled, and each question we pose opens a door to new revelations. How will our understanding of entanglement evolve? What new insights await us as we continue to probe the heart of this remarkable phenomenon? With each step into the realm of quantum mechanics, we are reminded of the wonder that surrounds us, a reminder that the universe is not merely a collection of separate entities, but a complex, interconnected whole. The story of quantum entanglement continues to unfold, inviting us to be active participants in the exploration of existence itself. Chapter 3. The Einstein-Podolsky-Rosen Paradox Unveiled. In the early days of quantum mechanics, a pivotal moment emerged from a paper published in 1935 by Albert Einstein, Boris Podolsky, and Nathan Rosen. This document, often referred to as the EPR paper, posed profound questions about the nature of reality itself. In their exploration, the trio sought to highlight what they perceived as inconsistencies within the framework of quantum mechanics. They introduced a thought experiment, one that would echo through the corridors of scientific discourse for decades. Their aim was to challenge the completeness of quantum mechanics and to bring forth a debate that continues to this day. Imagine two particles, entangled and separated by a great distance. According to quantum mechanics, measuring the state of one particle instantaneously influences the state of the other, regardless of the space that lies between them. In this scenario, Einstein-Podolsky-Rosen argued that such a phenomenon seemed to violate the principle of locality, which suggests that an object is only directly influenced by its immediate surroundings. Their conclusion was startling. If quantum mechanics required such instantaneous connections, then it could not be a complete description of physical reality. They implied the existence of hidden variables, unknown factors that could account for the observed phenomena without sacrificing the sanctity of locality. As we reflect on their argument, we might ask ourselves, what does it truly mean for something to be real? The EPR paper challenged the very essence of what we consider to be the fabric of reality. It was not merely a critique of quantum mechanics, but a philosophical inquiry into the nature of existence. Einstein, famously skeptical of the implications of quantum entanglement, once stated, "I cannot believe that God would choose to play dice with the universe." Through this lens, the EPR paper became not only a cornerstone of quantum theory, but also a catalyst for the exploration of deeper philosophical questions about determinism and the nature of the universe. As the scientific community absorbed the implications of the EPR paper, it ignited a vigorous debate among physicists. Many were drawn to the notion that locality, our understanding of how objects interact, might not hold in the quantum realm. It raised the question, can we truly trust our classical intuitions when faced with the peculiarities of quantum behavior? The tension between the EPR arguments and the prevailing quantum theories became a fulcrum around which discussions of reality and locality revolved. In the years following the publication of the EPR paper, responses from the quantum community began to surface. Some physicists embraced the challenge, seeing it as an opportunity to refine and deepen the understanding of quantum mechanics. Others, however, defended the existing framework, arguing that the EPR paper merely highlighted misunderstandings about quantum entanglement. The reactions varied from outright dismissal to spirited defense, each viewpoint contributing to an ongoing dialogue that would shape the future of physics. Niels Bohr, a leading figure in the quantum world, offered a counter-argument to the EPR paper. He emphasized that the act of measurement plays a vital role in determining the properties of quantum systems. According to Bohr, the peculiar behavior of entangled particles does not signify a deficiency in quantum mechanics, but rather highlights the unique nature of quantum reality itself. He asserted that the measurement process introduces a new layer of complexity that transcends classical notions of locality. In doing so, he shifted the focus from hidden variables to the relationship between observers and the systems they measure. What might it look like to embrace this new perspective? Consider the act of observing a sunrise. The colors that paint the sky are not merely reflections of light. They are influenced by atmospheric conditions, the observer's location, and even their emotional state. In a similar way, the measurement of a quantum system is not simply a passive act. It is an active engagement with the universe that shapes the reality being witnessed. This concept challenges us to think differently about the nature of observation and existence. As discussions continued, a pivotal moment arrived in the form of John Bell's theorem in the 1960s. Bell, intrigued by the implications of the EPR paper, formulated a set of inequalities that could be tested experimentally. If violated, these inequalities would suggest that no local hidden variable theory could explain the behavior of entangled particles. The quantum community braced itself for what would become a series of landmark experiments, each inching closer to unveiling the truth behind the EPR paradox. Imagine the anticipation surrounding these experiments, as scientists prepared to test the fabric of reality itself. The results consistently pointed toward the violation of Bell's inequalities, affirming the predictions of quantum mechanics and reinforcing the idea that entangled particles are indeed connected in ways that defy classical understanding. Each experiment brought with it a wave of excitement, a confirmation that the universe, at its core, is woven together in a manner that challenges our deepest intuitions. The implications of these findings were profound. They suggested that the universe does not adhere strictly to the principles of locality, as once believed. Instead, it hinted at a deeper interconnectedness, a bond that transcends space and time. This realization prompted physicists to revisit the foundational concepts of reality and locality, forcing them to reconsider the nature of measurements and the role of the observer. As we journey through this intricate landscape, we find ourselves faced with a question that resonates deeply. How do we reconcile our classical intuitions with the revelations of quantum physics? The answers are not straightforward, yet they illuminate the beauty and complexity of the universe. The EPR paradox and the subsequent discourse it inspired has not only broadened our understanding of quantum mechanics, but has also expanded our philosophical horizons. In the end, the EPR paper serves as a reminder of the ever-evolving nature of scientific inquiry. It embodies the spirit of curiosity that drives us to explore the unknown, to question the very nature of reality. Each challenge it presents invites us to delve deeper into the mysteries of the universe, to embrace the unknown with open hearts and minds. The debate surrounding the EPR paradox remains alive, a testament to the enduring quest for knowledge and understanding. As we continue to explore the implications of quantum entanglement and the EPR paradox, we are reminded of the words of Richard Feynman, who once said, "The imagination of nature is greater than the imagination of man." This sentiment echoes through the ages, urging us to seek knowledge and wonder in the vast expanses of the cosmos. Each discovery, each question, shapes our understanding and enriches the tapestry of human thought. In this unfolding narrative, as we ponder the nature of reality, we embrace the wonder of the unknown. The EPR paradox invites us to reflect on our place within the universe, to consider how the intricate connections between particles mirror the connections between ourselves. As we contemplate the vastness of existence, we find comfort in the knowledge that even the most profound mysteries can lead to a greater understanding of the world around us. The journey through the labyrinth of quantum mechanics is not merely an academic pursuit. It is a shared exploration of the nature of life itself. The discourse surrounding the EPR paper did not merely dwell within the confines of theoretical debate. It sparked a profound re-examination of the very principles that governed physics at the time. Scientists began to ponder the implications of entanglement beyond mathematical formalism, exploring its philosophical ramifications. The discussion stirred by the EPR paper invited a convergence of physics and philosophy, compelling thinkers to question the essence of reality itself. Among those drawn into this philosophical maelstrom was David Bohm, a theoretical physicist who sought to address the issues raised by the EPR paper from a different perspective. Bohm proposed an interpretation of quantum mechanics that resurrected the notion of hidden variables, yet his approach diverged from the traditional interpretations. He introduced the idea of a, quote, holo movement, suggesting that the universe is an interconnected whole where separateness is an illusion. His perspective offered a fresh lens through which to view the paradox, advocating that the apparent randomness in quantum mechanics could arise from deeper, underlying processes yet to be revealed. Consider how this resonates with our everyday experiences. When we observe a river, we see its flowing waters but rarely contemplate the unseen currents beneath the surface. Bohm's concept invites us to examine the depths of reality, where what lies beneath the observable may hold the key to understanding the mysteries of the universe. His alternative view posited that everything is inherently connected, challenging the notion of isolated events and encouraging us to embrace a more unified vision of existence. As the years unfolded, the quantum community grew increasingly divided. Some physicists rallied around the tenets of quantum mechanics as they stood, bolstered by experimental results that validated entanglement. Others, like Bohm, sought to reconcile the paradoxes that emerged from Einstein's critiques, leading to a more pluralistic view of reality. This lively debate illuminated the complexities at the heart of quantum mechanics, revealing that questions about existence were not merely academic, but rather deeply woven into the fabric of human thought and inquiry. One of the most compelling aspects of this discourse is the way it parallels advancements in technology. In recent times, the very principles that Einstein, Podolsky, and Rosen grappled with have paved the way for groundbreaking innovations. Quantum computing, for instance, harnesses the principles of superposition and entanglement, promising to revolutionize how we process information. Imagine computers capable of performing calculations at speeds unimaginable with classical devices, their power stemming from the very phenomena that challenged our understanding of reality. This convergence of thought and technology evokes a sense of wonder. How might the very fabric of our reality inform the tools we create? The exploration of these questions reveals that the legacy of the EPR paper extends far beyond academic discourse. It resonates in the tangible advancements we see today. As we delve into these advancements, we find ourselves pondering the implications of our newfound capabilities. What ethical considerations arise as we harness the power of quantum mechanics? The potential for quantum technology to redefine communication, security, and even our understanding of the universe itself compels us to reflect on the responsibilities that accompany such knowledge. Through the decades, the legacy of the EPR paper has continued to inspire scientists and philosophers alike. The debate over reality and locality is not confined to dusty archives, but has become a living dialogue, threading through the minds of those who dare to ask the difficult questions. This ongoing inquiry serves as a testament to the enduring nature of human curiosity and the quest for understanding. As we stand on the shoulders of giants like Einstein and Bohm, we are reminded of the words of Marie Curie, who once said, "Nothing in life is to be feared, it is only to be understood." Each question about the nature of reality beckons us to explore further, to embrace the unknown with courage and openness. The EPR paradox invites us to reconsider our place in the cosmos, urging us to seek knowledge while acknowledging the profound mysteries that remain. In this intricate dance of ideas, we are encouraged to cultivate a mindset that values inquiry over certainty. Each new discovery, each challenge to our understanding, propels us forward on a journey of exploration. The EPR paper stands as a beacon, illuminating the path toward deeper comprehension of the universe and our role within it. As we reflect on the implications of this dialogue, we find solace in the notion that the quest for knowledge is an inherent part of our existence. The interplay of reality and locality invites us to nurture our curiosity, to embrace the questions that arise in the face of uncertainty. In doing so, we honor the legacy of those who have come before us, while contributing our own threads to the ever-evolving narrative of understanding. The EPR paradox continues to resonate, challenging us to remain open-minded and adaptable as we navigate the complexities of the quantum realm. As we ponder the mysteries that await us, we are reminded that the journey of discovery is not merely an intellectual pursuit, but a shared experience that connects us all, binding us together in our quest for truth. Chapter 4. Experimental Evidence for Entanglement. In the realm of quantum mechanics, the notion of entanglement takes on a life of its own, transforming abstract ideas into tangible experiences that challenge our understanding of reality. As we journey through the experimental evidence for entanglement, we begin to witness a series of groundbreaking experiments that have shaped our comprehension of this remarkable phenomenon. One of the earliest and most significant experiments confirming entanglement is often referred to as the aspect experiment, named after physicist Alain Aspect. In the early 80s, Aspect set out to test the predictions of quantum mechanics against those of classical physics, specifically focusing on the implications of Bell's theorem. This theorem, proposed by physicist John Bell in the 60s, posited that if quantum mechanics is correct, then particles could be entangled in such a way that their properties would remain correlated, regardless of the distance between them. Imagine two entangled particles, separated by vast expanses of space, yet behaving as if connected by an invisible thread, sharing information instantaneously. The implications of Bell's theorem are profound, suggesting that the universe may not adhere to the classical notions of separateness and independence. Why is this significant? Because it challenges our classical intuitions about how the world should behave. Bell's theorem offers a testable distinction between quantum mechanics and theories that rely on local hidden variables. In essence, if experiments confirm the predictions of quantum mechanics, they would imply the existence of a deeper, non-local connection between entangled particles. Aspect's experiments involved pairs of entangled photons, which were sent in opposite directions toward two distant detectors. The results were striking. They consistently aligned with the predictions of quantum mechanics, supporting the idea that the measurement of one particle could instantaneously influence the other. These findings not only confirmed the entangled nature of the particles, but also sparked a cascade of further investigations into the implications of entanglement across various scientific fields. Imagine, if you will, the implications of this. The very fabric of reality seems to suggest that particles can communicate across distances, defying the limits imposed by the speed of light. This idea raises important questions about causality and our understanding of time and space. How can two particles, separated by light years, exhibit such synchronized behavior? The answer lies within the intricate web of quantum mechanics, where traditional rules do not apply. As we move forward in our exploration, we encounter the groundbreaking concept of quantum teleportation. This process, which may sound like something straight out of a science fiction novel, is a testament to the power of entanglement. Quantum teleportation allows for the transfer of quantum states between particles without any physical movement of the particles themselves. Picture this: two entangled particles, one with you and the other far away. By performing a measurement on your particle, you can instantaneously affect the state of the distant one. It is as though you are sending a message through the very fabric of the universe, one that transcends our traditional understanding of communication. The first successful demonstration of quantum teleportation occurred in the late 90s, when researchers at the University of Innsbruck in Austria successfully teleported the quantum state of a particle. This experiment relied on the entangled nature of photons, and the results were as mesmerizing as they were revolutionary. Imagine a world where information could be transmitted instantaneously, where secure communications could be achieved through the use of entangled particles. What might this mean for our technology, our understanding of privacy, and the very nature of information itself? Yet the journey does not end here. Real-world demonstrations of entangled particles continue to unfold, revealing the practical applications and implications of this phenomenon. Researchers have harnessed the power of entanglement to develop quantum computers, devices that could revolutionize computation by operating on principles far beyond the reach of classical computers. These quantum systems exploit the unique properties of entangled particles, allowing for calculations that were once deemed impossible. Consider the implications of a quantum computer. It could solve complex problems in seconds that would take classical computers millennia. The potential applications are vast, from drug discovery to cryptography, fundamentally altering industries and our approach to technology. This is not just theoretical. Teams around the globe are working tirelessly to bring quantum computers from the realm of speculation into practical use, with entanglement serving as one of the core pillars of this endeavor. Yet, while the scientific community continues to explore the depths of entanglement, the phenomena also evokes a sense of wonder and mystery. Researchers like Anton Zeilinger, a pioneer in the field, have articulated the philosophical implications of entanglement. He remarked that the phenomenon of entanglement shows us that we can no longer speak about the world in terms of isolated systems. This perspective invites us to reconsider our understanding of reality itself, prompting us to ponder the interconnectedness of all things. As we reflect on these ideas, we might ask ourselves, what does it mean for us as conscious beings inhabiting this universe? The implications of entanglement extend beyond physics, touching the realms of philosophy, consciousness, and even spirituality. The very act of observing and measuring in the quantum realm suggests a profound relationship between the observer and the observed, inviting us to explore the nature of our own existence within this spectacular framework. With each experiment, each demonstration of entangled particles, we peel back the layers of reality, revealing a world that is intricately woven together, a universe that dances to the rhythm of quantum mechanics. As we continue our journey, we find ourselves at the intersection of science and wonder, where the mysteries of the cosmos beckon us to dive deeper into the understanding of our reality. In this ever-evolving narrative, we stand on the brink of discovery, poised to unravel the secrets of entanglement and its far-reaching implications. The phenomena of entanglement not only invites us to explore the boundaries of science, but also encourages us to reflect on the very nature of our existence, the ties that bind us to the universe, and the infinite possibilities that lie ahead. The journey through the landscape of quantum mechanics continues as we delve into the heart of experimental evidence for entanglement, revealing not just the phenomena itself, but the enduring curiosity and relentless pursuit of knowledge by scientists around the globe. Each experiment conducted has been a step toward unraveling the intricacies of entanglement, illuminating the path toward a deeper understanding of our universe. One of the most remarkable experiments following the pioneering work of Alain Aspect was conducted by a team led by Nicholas Geeson in the late 90s. They took the concept of entanglement and tested it under real-world conditions, utilizing photons generated by a laser. These photons were sent through optical fibers to two separate locations, where they were measured simultaneously. The results echoed Aspect's earlier findings, once again confirming that the entangled particles behaved as if they were part of a single system, regardless of the distance that separated them. Imagine the elegance of this system: photons, delicate carriers of information, weaving through fibers, their destinies intertwined. When one photon was measured, the other responded instantaneously, as though they shared a secret language, a silent understanding that transcended the barriers of space and time. This experiment not only validated the principles of entanglement, but also marked a significant leap toward practical applications in quantum communication. In the realm of quantum communication, the implications of entanglement are profound. Researchers are investigating the potential of quantum key distribution, a method that leverages the principles of entanglement to create secure communication channels. Imagine a conversation where the mere act of eavesdropping could disrupt the entire exchange, making any attempt to intercept the information immediately detectable. This is the promise of quantum cryptography, a field that holds the potential to transform how we perceive privacy and security in an increasingly digital world. As we reflect on these advancements, we encounter the significance of Bell's theorem once more. It serves as a guiding beacon through the fog of uncertainty. The theorem not only provided a framework for testing the predictions of quantum mechanics against classical understandings, but also sparked a philosophical dialogue that resonates beyond the confines of physics. What does it mean for our understanding of reality when experiments consistently align with the predictions of quantum mechanics? Consider the implications of such a reality. If entanglement is a fundamental aspect of nature, it suggests that the universe is far more interconnected than we have been led to believe. This interconnectedness raises questions about locality, causality, and even the nature of consciousness itself. As physicist David Bohm once proposed, perhaps we are all part of a hollow movement, a unified whole, where separateness is merely an illusion. This perspective invites us to ponder our place in the cosmos, encouraging a deeper appreciation for the relationships that bind us to one another and to the universe. Moving forward, we find ourselves immersed in the concept of quantum teleportation. Building upon the foundational principles of entanglement, researchers have demonstrated not just the transfer of quantum states, but the potential for a new era of technological advancement. Imagine a future where information is not merely transmitted, but teleported from one point to another, with the implications echoing through fields as diverse as computing, medicine, and communications. In the early 2000s, scientists at the California Institute of Technology achieved a significant milestone in quantum teleportation, effectively transferring the quantum state of a photon to another distant photon. This achievement was not just a feat of engineering, but a profound demonstration of the capabilities inherent in entangled particles. With each successful teleportation experiment, we inch closer to realizing the dream of instantaneous communication and the profound potential it holds for humanity. As we consider these advancements, we might ask ourselves, what are the ethical implications of harnessing such power? The ability to transmit information instantaneously could reshape our understanding of data privacy, security, and even the nature of human interaction itself. It challenges us to think critically about how we wield this newfound capability, urging us to balance innovation with responsibility. Real-world demonstrations of entangled particles extend beyond the confines of laboratories. Across the globe, researchers are pushing the boundaries of what is possible with quantum technology. From satellite-based quantum communication systems to quantum networks designed for secure data transmission, the practicality of entanglement is beginning to manifest in ways that were once the realm of science fiction. Imagine a world where quantum satellites orbit the Earth, enabling secure communication channels that are impervious to eavesdropping. This is not a distant dream, but a burgeoning reality driven by the principles of entanglement. Countries are investing in quantum technology to ensure their security and technological supremacy, recognizing the pivotal role that entanglement plays in shaping the future. As we traverse this landscape of possibility, we are reminded of the words of physicist Richard Feynman, who once said, "The imagination of nature is far greater than the imagination of man." The exploration of entanglement invites us to stretch the limits of our understanding and to embrace the wonder that lies within the intricate workings of the universe. Each experiment, each revelation draws us closer to the essence of what it means to be part of this grand cosmic tapestry. The phenomenon of entanglement challenges our perceptions, urging us to reconsider how we relate to the universe and to one another. What mysteries lie yet undiscovered in the depths of this quantum realm? As we continue our exploration, we remain open to the possibilities that await us, eager to uncover the secrets of entanglement and its lasting impact on the future of science and humanity. Chapter 5: Quantum Entanglement and Information Theory. As we transition from the profound depths of experimental evidence into the intricate world of quantum computing, we find ourselves at the intersection of technology and the extraordinary properties of quantum entanglement. Imagine a realm where bits of information are no longer limited to the binary of zeros and ones, but instead can exist in a state of superposition, unlocking a new dimension of computational power. Quantum computing harnesses the principles of quantum mechanics, particularly entanglement, to perform calculations at speeds far beyond what is possible with classical computers. Entanglement serves as the backbone of quantum computing, allowing qubits, the fundamental units of quantum information, to become intertwined. Visualize a pair of qubits, intricately linked, where the state of one qubit is dependent on the state of its entangled partner. This relationship enables an exponential increase in processing capability. While a classical computer processes information sequentially, a quantum computer operates in parallel, exploring multiple possibilities simultaneously. This leap in efficiency could revolutionize fields ranging from cryptography to complex problem-solving, illuminating pathways to discoveries currently beyond our reach. The implications of entanglement extend far beyond computation and into the realm of security. Quantum cryptography, a burgeoning field, utilizes the principles of quantum mechanics to create communication channels that are inherently secure. Picture two parties wishing to communicate, sharing a secret key generated through the exchange of entangled particles. Because of the nature of quantum states, any attempt at eavesdropping would disturb the entangled system, alerting the communicating parties to the presence of an intruder. This feature of quantum cryptography is not merely theoretical. It offers a practical solution to the vulnerabilities of classical encryption methods, which can be susceptible to attacks from even the most sophisticated adversaries. As we delve deeper into the world of entangled states, we discover how they enhance information security. When two particles are entangled, measuring one immediately affects the other, regardless of the distance separating them. This phenomenon leads to the concept of quantum key distribution, a cornerstone of secure communication. Imagine a network built on the principles of quantum mechanics, where the very act of observation assures the safety of transmitted information. This transformative approach to security could render traditional hacking methods obsolete, providing a shield for sensitive data that is nearly impenetrable. The future of data transmission using entanglement holds boundless potential. Imagine a world where information travels not just through fibers or waves, but instantaneously across vast distances, thanks to the marvels of quantum entanglement. This concept, often referred to as quantum teleportation, allows for the transfer of quantum states from one particle to another without physically moving the particles themselves. It is as if information could be conjured from thin air, appearing at its destination as if it had always been there. The practical applications of such technology could transform how we communicate, share information, and conduct transactions. Consider the implications for global finance, where secure transactions could occur instantaneously, free from the frailties of distance and delay. The prospect of a quantum internet, built on the principles of entanglement, could redefine our understanding of connectivity. We would no longer be limited by the physical boundaries of our current technologies, allowing for a truly interconnected world. In this unfolding narrative of quantum entanglement, we encounter remarkable figures who have dedicated their lives to unlocking its mysteries. One such individual is Charles Bennett, a pioneer in the field of quantum cryptography. His work has laid the foundation for developing secure communication systems that utilize entanglement as a core principle. Bennett once remarked that the most important aspect of quantum mechanics is not the mechanics, but the information. This perspective emphasizes the central role of information theory in understanding and leveraging the potential of quantum entanglement. As we reflect on these developments, we may ask ourselves, how will our world change as we adopt these technologies? Will our understanding of privacy and security evolve alongside these advancements? The answers to these questions lie at the heart of an exciting future, one where the boundaries of technology and the principles of quantum mechanics converge, offering new possibilities and challenges. The journey into the depths of quantum entanglement and its applications is just beginning. We stand on the brink of a new era where the synergy between quantum mechanics and information theory could redefine our interactions with the world. Imagine a landscape transformed by instantaneous communication, secure transactions, and a deeper understanding of the fabric of reality itself. This vision, once confined to the realms of science fiction, is becoming increasingly tangible, inviting us to explore the possibilities that lie ahead. The intricate web of quantum computing continues to expand as researchers delve deeper into the potential of entanglement. Imagine the elegance of a quantum algorithm, where entangled qubits work together to solve complex problems that would take classical computers eons to unravel. Quantum algorithms, like Shor's algorithm for factoring large numbers or Grover's algorithm for searching unsorted databases, take advantage of entanglement to perform tasks exponentially faster than their classical counterparts. This leap in capability not only opens doors for advancements in fields such as cryptography and optimization, but also poses intriguing questions about the limits of computation itself. What if problems that were once deemed intractable could be solved with relative ease? In the realm of quantum cryptography, the implications of entanglement grow even more profound. The exchange of entangled particles creates a system of communication that is not merely secure, but fundamentally different from classical communication channels. Imagine a conversation where every word is impervious to eavesdropping, where the very act of listening disturbs the message. This unique property of entangled states underpins the security of quantum key distribution protocols, such as BB84, ensuring that any attempt to intercept the key will be detected. This is a groundbreaking shift in how we approach the security of information in an increasingly digital world. As we consider the future of data transmission, we must also ponder the concept of quantum teleportation. This phenomenon, often misunderstood, does not involve the instantaneous transportation of matter, but rather the transfer of information regarding the quantum state of a particle from one location to another, facilitated by entanglement. Picture a scenario in which a quantum state is created in one location, and through the entangled nature of particles, that state is perfectly reproduced at a distant location, without the original state ever leaving its place. This process could revolutionize communication networks, making them faster and more secure than ever before. The possibilities for future applications of quantum entanglement are vast. Researchers are exploring the potential of a quantum internet, a network that would harness the power of entanglement to create an ultra-secure communication infrastructure. Imagine a world where data is transmitted not through traditional channels, but through a network of entangled particles, allowing for instantaneous connections across the globe. This quantum internet would not only enhance security, but also improve efficiency, enabling real-time communication and collaboration regardless of distance. In this landscape of innovation, we encounter visionaries like David Deutsch, a pioneer in the field of quantum computing. Deutsch's insights into the nature of computation and information have paved the way for a deeper understanding of how quantum mechanics can be applied to solve practical problems. He once stated, "The universe is not just a place, but a network of information." His perspective encourages us to view the universe as a dynamic interplay of information, where the principles of quantum mechanics and information theory merge seamlessly. As we explore these emerging technologies, we may find ourselves reflecting on the implications of such advancements. How will our understanding of privacy evolve in an era where communication is shielded by the principles of quantum mechanics? Will we redefine our relationship with information, recognizing it as something that can be transmitted securely and instantaneously? The answers to these questions will shape the ethical landscape of the future, guiding our interactions with technology and each other. In tandem with these advancements, we also face challenges. The development of quantum technologies necessitates a robust understanding of the underlying principles and potential pitfalls. For instance, the phenomenon of decoherence poses significant hurdles for practical quantum computing. As qubits interact with their environment, they can lose their delicate entangled states, leading to errors in computation. Researchers are tirelessly working on error correction techniques and methods to isolate qubits from environmental noise, striving to create stable systems capable of harnessing the full power of entanglement. Imagine the day when quantum computers are fully realized, functioning seamlessly in our daily lives. What new frontiers will we explore as we harness the power of entanglement? The potential applications in medicine, materials, science, and artificial intelligence are only beginning to be understood. As we embrace these changes, we must remain mindful of the ethical considerations surrounding such transformative technologies, ensuring that the benefits are equitably distributed. Quantum entanglement is not merely a fascinating phenomenon confined to the laboratory. It represents a paradigm shift in our understanding of the universe and the nature of information itself. As we stand on the precipice of this quantum revolution, we can envision a future where the boundaries of communication, computation, and security are redefined. The journey into the depths of entanglement continues, inviting us to explore the limitless possibilities that lie ahead, guided by the principles of quantum mechanics and the vision of those who dare to dream. The role of entanglement in quantum computing is not merely a fascinating aspect of theoretical physics. It serves as a practical foundation for developing technologies that could redefine our world. Imagine a system where the power of computation is not limited by the constraints of classical systems. Instead, through entangled qubits, information processing occurs at remarkable speeds, enabling solutions to complex problems that were once deemed insurmountable. For instance, researchers are exploring the potential of quantum algorithms to optimize logistics and supply chains, potentially revolutionizing industries that rely on efficiency and speed. As we consider the implications of quantum cryptography, we begin to appreciate a new paradigm in secure communication. The entangled states not only offer a unique method of generating secure keys, but also create a new landscape for privacy. Visualize a world in which personal communications and financial transactions are shielded from prying eyes, ensuring confidentiality in an increasingly interconnected digital age. The principles of entanglement provide a bulwark against potential threats, safeguarding our most sensitive information against even the most sophisticated cyber attacks. Entangled states enhance information security in ways that classical systems cannot replicate. When we think about traditional encryption methods, they often rely on mathematical complexity that could potentially be unraveled by future advancements in computing power. Quantum cryptography, however, operates on the fundamental laws of physics. The inherent properties of entangled particles allow for the detection of eavesdropping attempts in real time. Imagine a scenario where every attempt to intercept a communication yields immediate awareness of the breach, empowering individuals and organizations to take swift action. This transformative capability positions quantum cryptography as a vital tool in preserving the integrity of sensitive data. Looking to the future, the prospect of data transmission through quantum entanglement offers a tantalizing vision of instantaneous connections across the globe. Picture a quantum internet, a network where information can traverse vast distances without the constraints of traditional infrastructure. This quantum realm could enable real-time collaboration across continents, bridging gaps that currently exist in our global communication systems. Such advancements would not only enhance personal interactions, but also foster new avenues for international cooperation in scientific research and development. The potential applications of this technology extend far beyond secure communication and rapid data transmission. Imagine breakthroughs in medicine, where quantum computing accelerates drug discovery by simulating molecular interactions with unprecedented accuracy. Or consider the impact on climate modeling, where complex simulations can be run in record time, leading to more effective strategies for addressing global challenges. The integration of quantum entanglement into these fields could catalyze innovations that alter the course of human progress. As we explore these possibilities, we encounter the visionaries and pioneers who are shaping the future of quantum technologies. One such figure is Love Grover, who developed Grover's algorithm, demonstrating how quantum computing can significantly enhance search capabilities. His work illustrates the profound implications of entanglement in processing information, making it clear that we are just beginning to scratch the surface of what is possible. Grover once noted, "The more we learn about quantum mechanics, the more we learn about ourselves." This statement serves as a reminder that our understanding of quantum phenomena not only expands our technological horizons, but also deepens our insight into the very nature of existence. As we stand on the brink of this quantum revolution, the questions we face are both profound and essential. How will society adapt to these changes? What ethical frameworks will guide our interactions with these powerful technologies? The implications of quantum computing, cryptography, and data transmission stretch far beyond the realm of science and technology, touching upon issues of privacy, security, and the fundamental nature of information itself. In this unfolding narrative, the journey into quantum entanglement continues to beckon us forward. Each advancement brings with it new questions and challenges, urging us to remain vigilant as we navigate the complexities of this brave new world. With every step, we are invited to imagine a future shaped by the principles of quantum mechanics, where the boundaries of what is possible are continually redefined, and where our connection to the universe is illuminated by the light of innovation and understanding. Chapter 6. Entanglement in Quantum Communication Systems. Imagine a world where communication transcends the limitations of distance and time, a realm shaped by the principles of quantum mechanics. This emerging field of quantum communication technologies harnesses the peculiarities of the quantum world, promising secure and instantaneous transfer of information. As we explore this captivating domain, we uncover the foundational elements that make quantum communication not just a theoretical dream, but a burgeoning reality. At the heart of quantum communication is the concept of quantum key distribution, an ingenious method that enables two parties to securely share cryptographic keys. Picture two friends sitting far apart, each wanting to send messages to the other without the fear of interception. With classical communication, a third party could easily eavesdrop, taking advantage of the signals traveling through wires or airwaves. However, in the quantum realm, any attempt to observe the keys being exchanged disrupts their state. This is because, as we learned in our previous discussions, quantum systems are delicate, and any measurement inevitably alters their properties. The beauty of quantum key distribution lies in its ability to detect eavesdropping attempts. The moment someone tries to intercept the key, the system alerts the sender and receiver, allowing them to abandon the compromised key and attempt a new exchange. Imagine that moment of realization, the assurance that the communication remains secure because of the very nature of the particles involved. This innovative approach has been propelled into real-world applications, with prototypes already operational. Various institutions and companies are pioneering this technology, demonstrating its potential across a myriad of sectors, from secure banking transactions to protecting sensitive governmental communications. One notable example is China's quantum satellite, Mikius, launched to facilitate secure quantum communications between ground stations. This satellite is a testament to human ingenuity, reaching heights that allow it to establish connections across vast distances, all while employing the principles of quantum mechanics to ensure the integrity of the communication. Yet, as we bask in the promise of quantum communication, it is essential to acknowledge the challenges that lie ahead. Implementing quantum communication systems is no small feat. The delicate nature of quantum states makes them susceptible to various forms of interference, which can lead to loss of information. To visualize this, imagine a serene lake where ripples disturb the stillness. Any disturbance affects the clarity of the water. Similarly, in quantum systems, environmental factors can disrupt the coherence of quantum states, rendering communication ineffective. Moreover, the infrastructure required for quantum communication systems demands significant advancements. The existing communication networks, predominantly built on classical principles, would need to be reimagined to integrate quantum technologies seamlessly. This transformation entails not only technological innovations, but also substantial investment and collaboration across different sectors. As physicist and pioneer in quantum communication Nicholas Geeson once noted, "The quantum world is not only beautiful, it is also practical. The hurdles do not end there." Quantum communication requires an intricate understanding of quantum entanglement, which serves as the backbone for many of these technologies. As we have previously explored, entanglement creates a unique correlation between particles, allowing them to share information instantaneously. However, harnessing this property in real-world applications is a complex endeavor. Designing systems that can effectively generate and maintain entangled states over long distances remains a significant challenge. As we ponder the future of quantum communication, we can find solace in the strides made by researchers and engineers dedicated to overcoming these obstacles. Consider the ambitious efforts in quantum repeaters, devices designed to extend the range of quantum communication by entangling particles over long distances. These repeaters act as intermediaries, creating new entangled pairs that can bridge the gaps between users. It's a fascinating endeavor, akin to building a bridge across an expansive chasm connecting two distant lands. Imagine the implications of successful quantum communication systems. They could redefine our understanding of privacy and security, enabling unbreakable codes and revolutionizing how sensitive information is shared. The potential benefits extend beyond mere communication. They could enhance the fields of quantum computing and cryptography, providing the foundation for a new era of technological advancement. As we navigate this intricate landscape, it is essential to recognize the ongoing efforts of scientists and engineers who are tirelessly working to translate theory into practice. Each advancement is a testament to human creativity and determination, pushing the boundaries of what is possible. The journey is marked by a series of incremental successes, each contributing to the overarching goal of establishing reliable quantum communication systems. While we contemplate the future, we can also reflect on the profound philosophical implications that quantum communication presents. What does it mean for our understanding of information, privacy, and trust in the digital age? As we engage with these questions, we find ourselves at the intersection of science and ethics, pondering the responsibilities that come with such powerful technologies. As we continue to explore the landscape of quantum communication, we are reminded of the vast potential that lies ahead. The quest for secure communication systems, grounded in the principles of quantum mechanics, beckons us to envision a world where information flows freely and securely, transcending barriers that once seemed insurmountable. Each step forward brings us closer to unlocking the secrets of the quantum realm, painting a picture of a future rich with possibility. In the landscape of quantum communication, the concept of quantum key distribution is just the beginning. As we further explore the capabilities of quantum technologies, we find ourselves drawn to the intricate web of applications that extend far beyond mere secure messaging. Imagine a world where quantum communication systems can facilitate complex transactions in an instant, ensuring data integrity across global networks. This vision is becoming increasingly tangible as researchers and engineers continue to push the boundaries of what is possible. One of the most promising applications of quantum communication lies within the realm of secure financial transactions. Picture a bustling stock exchange where information is exchanged at lightning speed. In such an environment, the security of data is paramount. Quantum communication can establish a secure link between trading partners, ensuring that sensitive information remains protected from prying eyes. This is not just a theoretical proposition. Pilot projects are already underway in various financial institutions, testing the viability of quantum networks to safeguard trades. In the medical field, the potential applications of quantum communication are equally compelling. Consider the transmission of sensitive patient data between hospitals and laboratories. The confidentiality of medical records is vital, and quantum key distribution can enhance the protection of this information. By employing quantum communication systems, healthcare providers can ensure that patient data remains secure during transmission, fostering trust in digital health technologies. Moreover, the implications extend to national security. Governments are increasingly recognizing the importance of quantum communication in safeguarding classified information. Imagine military communications that utilize the principles of quantum entanglement to transmit orders and intelligence securely. Such systems could protect against cyber threats, rendering interception attempts futile. Countries around the world are investing in quantum research, striving to develop communication networks that can withstand sophisticated hacking techniques, ultimately ensuring the integrity of their national security frameworks. Yet despite the excitement surrounding these advancements, we must confront the significant hurdles that lie in the path of widespread adoption. The integration of quantum technologies into existing infrastructures presents a formidable challenge. Envision a vast, intricate highway system that needs to accommodate a new type of vehicle, one that operates under entirely different rules. Upgrading communication networks to incorporate quantum capabilities requires not only new hardware, but also the development of protocols that can seamlessly bridge the classical and quantum realms. One of the primary issues affecting implementation is the fragility of quantum states. As we touched upon earlier, environmental factors can disrupt the delicate balance required for effective quantum communication. These disturbances can lead to what is known as decoherence, a phenomenon where entangled states lose their correlations due to interaction with the environment. Imagine a delicate flower wilting under harsh sunlight. Similarly, quantum states can degrade when exposed to external noise. To combat these challenges, researchers are exploring various methods, including error correction techniques and the development of more robust quantum technologies. Additionally, the question of scalability looms large. As quantum networks expand, maintaining the integrity of entangled states across vast distances becomes increasingly complex. The idea of quantum repeaters, which we briefly touched upon, serves as a beacon of hope in this regard. These devices are designed to regenerate quantum signals over long distances, ensuring that communication remains uninterrupted and secure. However, the technology is still in its infancy, and significant advancements are needed to realize the full potential of quantum repeaters in practical applications. As we reflect on the trajectory of quantum communication systems, the contributions of notable pioneers in the field remind us of the human spirit's relentless pursuit of knowledge. Scientists like Charles Bennett and Arthur Eckert have played pivotal roles in shaping the landscape of quantum cryptography. Bennett, known for his work on the BB84 protocol, revolutionized the way we think about secure communication. His insights into the relationship between quantum mechanics and information theory laid the groundwork for the practical application of quantum key distribution. Eckert, on the other hand, introduced the concept of entanglement-based quantum key distribution, further expanding our understanding of how entanglement can be harnessed for secure communication. His work has inspired a new generation of researchers to explore the intersection of quantum mechanics and information security. The words of Eckert resonate deeply. Quantum mechanics introduces a new way of looking at communication, where the very act of observation changes the outcome. This idea encapsulates the essence of quantum communication, where observation and interaction play a fundamental role in the realization of secure transmission. As we stand on the cusp of a new era in communication technology, we are compelled to consider the broader implications of these advancements. The ethical considerations surrounding quantum communication remain a topic of fervent discussion. How will society adapt to the new standards of privacy and security that quantum technologies promise? The answers to these questions are far from straightforward, yet they remind us that with great power comes great responsibility. Imagine for a moment a world transformed by quantum communication, a landscape where the flow of information is governed by the principles of quantum mechanics, offering unprecedented levels of security and efficiency. The possibilities are as vast as the universe itself, inviting us to ponder what lies ahead. As we navigate this uncharted territory, we are reminded of the delicate balance between innovation and ethics, prompting us to tread carefully as we forge ahead. Each breakthrough in quantum communication brings us closer to unlocking the secrets of the universe, intertwining science, technology, and philosophy in a dance of discovery. The journey is ongoing, and as we continue to unravel the mysteries of the quantum realm, we move ever closer to a future where secure communication systems reshape our understanding of information itself. Chapter 7. Applications of Entanglement in Technology. As we venture into the applications of quantum entanglement in technology, we find ourselves surrounded by a landscape rich with promise and innovation. The principles of entanglement, once confined to theoretical discussions and experimental pursuits, now extend their tendrils into various facets of our technological future. Among the most captivating applications lies the realm of quantum sensors, which harness the delicate properties of entangled particles to achieve unprecedented precision. Imagine a sensor capable of detecting minute changes in the environment, such as the faintest vibrations or the slightest shifts in temperature. Quantum sensors utilize entanglement to enhance their sensitivity beyond the limits of classical devices. By employing entangled particles, these sensors can measure physical quantities with a precision that was once thought unattainable. This heightened sensitivity opens doors to a myriad of applications, from medical imaging to geophysical exploration. For instance, consider the potential for detecting early signs of disease through subtle changes in biological signatures. Such advancements could revolutionize diagnostics, providing healthcare professionals with tools to catch illnesses at their nascent stages, ultimately saving lives. In the realm of communication, the role of entanglement in developing quantum networks stands as a marvel of modern science. These networks promise to redefine how we exchange information, ensuring that data travels securely and swiftly across vast distances. Imagine a network where information is transmitted instantaneously, unbound by the constraints of conventional communication. Quantum entanglement forms the backbone of this vision, enabling nodes within the network to share information in a manner that is inherently secure. The interconnectedness of entangled particles allows for the creation of quantum repeaters, which extend the range of quantum communication without compromising security. This capability is crucial in a world increasingly reliant on data, where safeguarding sensitive information has never been more vital. As we traverse the landscape of technology further, we encounter the exciting potential of quantum entanglement in advancing artificial intelligence. Picture artificial intelligence systems that harness the power of entangled qubits, allowing them to process information in ways that classical systems cannot. The fusion of quantum mechanics and AI could lead to breakthroughs in machine learning, where entangled states facilitate faster and more efficient data analysis. The implications are profound. Algorithms that once took considerable time to train could reach conclusions in a fraction of that duration. This leap in efficiency could empower AI applications across various sectors, from healthcare to finance, enabling them to make predictions and decisions with remarkable accuracy. The impact of quantum entanglement extends beyond sensors and communication. It permeates the realm of material science and research. Imagine scientists able to probe the properties of materials at an atomic level with unparalleled precision, revealing insights that were previously hidden to classical methods. Quantum entanglement enables researchers to explore the behavior of materials under various conditions, unlocking new avenues for innovation in fields such as nanotechnology and superconductors. The ability to manipulate and understand materials at their fundamental level could lead to the development of new substances with extraordinary properties, paving the way for advancements in energy storage, electronics, and beyond. Among the luminaries in the field, physicist Anton Zeilinger has been at the forefront of research on quantum entanglement and its applications. His pioneering work has illuminated how entangled states can be harnessed for practical purposes, transforming the abstract into the tangible. Reflecting on the potential of quantum technology, he stated, "What we are trying to do is to make use of quantum mechanics to create a new technology. This vision serves as a guiding star for researchers and innovators, inspiring them to explore the vast possibilities that entanglement offers." As we consider the implications of these technologies, one might wonder how far we can truly go with quantum entanglement. What new avenues of exploration await us in the years to come? The answers may lie in the continued collaboration between scientists, engineers, and visionaries who dare to dream of a world woven together by the principles of quantum mechanics. The unfolding narrative of quantum technology is not just about machines and algorithms. It is about reimagining how we interact with the universe itself, revealing the profound connections that bind us all. In this ever-evolving landscape, the quest for understanding and harnessing quantum entanglement continues. Each breakthrough in quantum sensors, networks, artificial intelligence, and material science brings us closer to a future where the mysteries of the quantum world are not merely theoretical, but integral to our everyday lives. As we stand on the cusp of this new era, the possibilities seem endless, inviting us to imagine the extraordinary transformations that lie ahead. As we delve deeper into the impressive applications of quantum entanglement, we find ourselves at the exciting frontier of quantum sensors. Building on the idea of heightened sensitivity, these devices exploit the unique properties of entangled particles to unlock new dimensions of measurement. Imagine a quantum sensor designed to detect gravitational waves, the ripples in space-time that were first predicted by Einstein and later confirmed by groundbreaking experiments. The interplay of entangled photons within these sensors can lead to the discovery of previously undetectable phenomena, enabling scientists to probe the universe at scales that were once thought unreachable. Consider the implications of such advancements in various fields, particularly in astrophysics and navigation. Quantum sensors could revolutionize our understanding of cosmic events, providing insights into the formation of black holes or the behavior of neutron stars. The ability to measure gravitational waves with unprecedented accuracy opens a window into the very fabric of the universe, enabling us to witness its most dramatic events as they unfold. In addition to their role in astrophysics, quantum sensors can also enhance our capabilities in Earth monitoring. Envision a world where we can detect subtle changes in the Earth's magnetic field, providing early warnings for natural disasters such as earthquakes or tsunamis. This proactive approach to disaster management could save countless lives and mitigate the devastating impacts of such events. The fusion of quantum entanglement with sensor technology not only enriches our scientific toolkit, but also serves as a beacon of hope for a safer future. Transitioning from sensors to the intricacies of communication, we encounter the realm of quantum networks, a domain where entanglement plays a pivotal role. Imagine a global network of quantum devices, each connected through entangled particles, facilitating communication that is not only instantaneous, but also secure against eavesdropping. This vision of a quantum internet could redefine how we share information, creating a framework where data is transmitted with a level of safety that classical systems cannot offer. The development of quantum networks hinges on the concept of entangled photons being shared across vast distances. Picture a scenario where two parties, separated by continents, can communicate in real time, their messages safeguarded by the very nature of entanglement. This security is rooted in the principle that any attempt to intercept or measure the entangled particles would disrupt their state, alerting the communicating parties to potential breaches. As we explore this technological tapestry further, it becomes clear that quantum networks will not only enhance privacy, but also support a myriad of applications, ranging from secure banking transactions to confidential communications in governmental and military operations. The ability to transmit information in a way that is fundamentally secure alters our approach to data integrity and confidentiality, ushering in a new era of digital interaction. Now let us ponder the intersection of quantum entanglement and artificial intelligence. Imagine a future where AI systems are enhanced by the capabilities of quantum computing, powered by entangled qubits. The synergy between AI and quantum mechanics promises to unlock new dimensions of processing power. Think of algorithms capable of analyzing vast datasets at unprecedented speeds, drawing insights that were previously beyond our reach. This fusion of technologies could lead to breakthroughs in fields such as personalized medicine. Picture AI systems analyzing genetic information and medical histories, predicting the most effective treatments for individual patients based on their unique profiles. The entangled states within quantum processors could facilitate complex simulations, allowing for rapid exploration of various treatment scenarios, ultimately leading to enhanced outcomes and a deeper understanding of human health. The implications of this synergy extend into the realm of climate modeling as well. Imagine AI systems utilizing quantum-enhanced data processing to predict climate patterns with remarkable precision, identifying potential consequences of climate change and informing policy decisions. The ability to harness quantum entanglement in AI could empower us to tackle some of the most pressing challenges facing humanity, providing tools that enhance our capacity for understanding and action. Finally, we arrive at the influence of quantum entanglement on material science, a field that stands to benefit immensely from these advancements. Imagine researchers armed with quantum sensors capable of probing materials at the atomic level, revealing properties that classical techniques could never uncover. This newfound understanding could drive innovation in various industries, from electronics to renewable energy. Consider the development of new materials with properties tailored for specific applications, such as superconductors that operate at higher temperatures or batteries that store energy more efficiently. As scientists delve into the atomic interactions within materials, guided by the insights provided by entanglement, they may uncover pathways to breakthroughs that change the very nature of technology as we know it. The journey through the applications of entanglement reveals a landscape rich with possibilities, where each discovery seems to beckon us toward a future filled with promise. As we explore these technologies, we are reminded of the words of physicist Niels Bohr, who once said, "We are not only a part of the universe, we are the universe." This interconnectedness resonates deeply within the fabric of quantum entanglement, urging us to recognize the profound implications of our advancements, not just for technology, but for the very essence of our existence. What lies ahead in this symphony of quantum possibilities? The answer is as vast as the universe itself, waiting to be unraveled by those who dare to dream and explore. With each step forward, we draw closer to a reality where the wonders of quantum mechanics enrich our lives, illuminating the path to a future shaped by innovation and discovery. The exploration of quantum entanglement further unveils its potential in revolutionizing artificial intelligence, a field that is rapidly evolving and seeking new horizons. Consider the prospect of AI systems that leverage the unique capabilities of quantum computing, where entangled qubits work in harmony to process information at unprecedented speeds. Imagine these systems sifting through vast oceans of data, discerning patterns and drawing insights with a level of sophistication that far exceeds classical computational power. This synergy between quantum mechanics and AI could lead to transformative applications. For instance, in the realm of healthcare, AI models might analyze genetic data and medical histories, tailoring treatments to individual patients with remarkable precision. The entangled states of qubits could facilitate simulations that allow scientists to explore myriad treatment options, optimizing outcomes in ways that classical systems could only dream of achieving. Moreover, envision how this integration could influence fields such as logistics and supply chain management. An AI system enriched by quantum capabilities could analyze complex variables in real time, enhancing decision-making processes and improving efficiency across industries. The ability to predict demand fluctuations or optimize routes could substantially reduce costs and waste, fostering a more sustainable future. As we journey deeper into the applications of entanglement, we cannot overlook its profound implications for material science. Imagine the possibilities when researchers can manipulate materials at the atomic level with the precision afforded by quantum technologies. Quantum entanglement opens up new pathways for discovery, allowing scientists to probe the properties of materials in ways that classical techniques simply cannot achieve. Consider the development of advanced materials that could revolutionize energy storage. Researchers are exploring the potential of superconductors that operate at higher temperatures, a breakthrough that could lead to more efficient power grids and lossless energy transmission. The insights gained from quantum-level examinations may unveil novel materials with extraordinary properties, such as enhanced conductivity or unique magnetic behaviors, paving the way for innovations in everything from electronics to renewable energy technologies. As we reflect on the journey through these diverse applications, the interconnectedness of quantum entanglement and technological advancement becomes increasingly evident. Each breakthrough serves as a stepping stone toward a future where the boundaries of what is possible are continually expanded. The words of physicist Richard Feynman resonate profoundly in this context. The most important thing is not to stop questioning. Curiosity has its own reason for existence. This spirit of inquiry fuels the exploration of entanglement's potential, encouraging us to remain open to the myriad possibilities that lie ahead. What transformative technologies await us as we continue to harness the principles of quantum mechanics? The unfolding narrative of entanglement in technology is not merely a tale of scientific progress. It is a testament to our relentless pursuit of understanding and innovation, urging us to envision a world where the wonders of the quantum realm enrich our lives and reshape our realities. In this ever-evolving landscape, the interplay between quantum entanglement and technology invites us to dream, explore, and engage with the universe in ways we have yet to fully comprehend. Chapter 8. Philosophical Implications of Entanglement. In the heart of quantum mechanics lies a phenomenon that challenges our most fundamental beliefs about separability. Entanglement presents a striking contradiction to our everyday experiences, where objects are perceived as distinct entities, operating independently within their own realms. Imagine a pair of shoes, each existing in its own space, yet designed to complement one another perfectly. In the quantum world, however, the situation is far more intricate. When two particles become entangled, their fates intertwine in such a way that measuring one immediately influences the other, regardless of the distance that stretches between them. This profound connection raises a pivotal question. What does it mean for something to be separate? Are we merely observing a facade of individuality? Or is there a deeper interconnectedness that underpins our reality? The implications of entanglement extend far beyond the realm of physics, inviting us to reconsider concepts of determinism and free will. Throughout history, the debate surrounding these ideas has captured the imaginations of philosophers and scientists alike. Determinism suggests that every event in the universe is the result of preceding events, a chain of cause and effect that unfolds with clockwork precision. In contrast, free will posits that individuals possess the agency to make choices, shaping their destinies in a world that may not be as rigidly predetermined as it appears. Entanglement, with its inherent unpredictability, raises questions about the very nature of choice. If particles can instantaneously affect each other across vast distances, what does this imply for our understanding of decision-making? Are our thoughts and actions merely the result of entangled interactions within our environment? Or do we possess an autonomous will that transcends such connections? Consider the words of a prominent thinker in the field, who once mused about the implications of quantum mechanics on our understanding of reality. This evokes a profound image of a web where every thread is connected, influencing the others in ways that defy the linear causality we often rely on. Entanglement invites us to ponder whether our experiences and choices are part of a grander scheme, one that we are only beginning to understand. As we reflect on these themes, we find ourselves drawn into a deeper consideration of reality itself. The implications of entanglement challenge not only our scientific paradigms, but also our philosophical interpretations of existence. What does it mean for something to be real? The classical view posits that reality consists of distinct objects existing independently in space and time. Yet, as we explore the entangled nature of particles, we encounter a more holistic perspective, where boundaries blur and separateness dissolves. Imagine a vast ecosystem, where every organism influences its neighbors, creating a delicate balance that sustains life. In much the same way, entangled particles interact in a dance of probabilities, reminding us that the fabric of reality may be woven from threads of connection rather than isolation. This vision of interconnectedness holds profound implications for our understanding of existence. How might we redefine our relationship with the universe, acknowledging that we are not merely observers but participants in a complex web of interactions? The influence of entanglement extends into the realm of philosophical discourse, where it has sparked vibrant debates among thinkers across various disciplines. From metaphysics to ethics, the concept of entanglement serves as a bridge between science and philosophy, inviting exploration into the nature of consciousness, identity, and moral responsibility. If our thoughts and actions are interwoven with those of others, how does this shape our understanding of ethics? Are we accountable for our choices, or are they reflections of a greater interconnected reality? As we journey further into this philosophical landscape, we encounter the intriguing notion of non-locality, a cornerstone of entanglement. Non-locality suggests that the effects of entangled particles are not confined by the limitations of space or time, defying classical intuitions. This concept challenges us to reconsider our understanding of causation, prompting questions about the nature of influence and interaction. Imagine a ripple in a pond, where one disturbance creates waves that reach distant shores, subtly altering the environment. In much the same way, entangled particles communicate across distances, reshaping our perceptions of reality. The implications of non-locality extend to our understanding of consciousness as well. Some philosophers propose that consciousness itself may be a manifestation of entangled interactions within the brain, where neurons communicate in ways that transcend traditional boundaries. This perspective invites us to explore the possibility that our very thoughts may be interconnected, echoing the entangled nature of the universe itself. Are we, in essence, reflections of a greater cosmic consciousness shaped by the entangled interactions of the universe? As we contemplate these profound questions, we find ourselves standing at the intersection of science and philosophy, where the mysteries of entanglement beckon us to explore uncharted territories. The implications of this phenomenon extend beyond the confines of the laboratory, inviting us to engage with the very essence of our existence. As we delve deeper into the philosophical repercussions of entanglement, we can't help but wonder how these ideas resonate with our daily lives. The concept of interconnectedness, once confined to the realm of quantum physics, finds its way into our relationships, our communities, and our understanding of the world around us. Imagine a community where every individual recognizes the influence of their actions on others, fostering a sense of collective responsibility and empathy. How might this shift in perspective change the way we approach our interactions, our decisions, and our understanding of ourselves? Entanglement thus serves as a profound metaphor for the interconnectedness of human experience. In a world where we often perceive ourselves as isolated beings, the principles of quantum mechanics invite us to reconsider our relationships with one another and with the universe. The recognition of our entangled existence encourages a sense of unity, a call to embrace the collective nature of our experiences. As we stand on the precipice of these philosophical explorations, we are reminded of the words of a great thinker who once remarked on the importance of understanding the world in its entirety. This perspective resonates deeply with the idea that, much like particles in the quantum realm, our lives are intertwined in a complex web, rich with potential and possibility. In this light, the conversation surrounding entanglement transcends the boundaries of scientific inquiry, inviting us to engage with the fundamental questions of existence. What does it mean to be human in an entangled universe? How do we navigate our lives when the lines between self and other blur? These questions echo through the halls of philosophy, inviting ongoing dialogue and contemplation. As we continue to explore the philosophical implications of entanglement, we may find ourselves drawn to the notion of collective consciousness. This concept suggests that our thoughts, emotions, and experiences are not merely individual phenomena, but rather part of a shared tapestry of existence. Imagine a vast ocean where every drop contributes to the greater whole, shaping the currents and tides. In this way, our individual lives may be seen as integral threads in the larger fabric of reality, influencing one another in ways that extend beyond our immediate perceptions. In the realm of ethics, this interconnectedness raises questions about moral responsibility and accountability. If our actions are influenced by the entangled nature of existence, how do we define right and wrong? Are we responsible for the consequences of our choices, or are they simply reflections of a greater network of interactions? These inquiries challenge us to rethink our understanding of morality, urging us to embrace a more compassionate and inclusive perspective. The philosophical implications of entanglement also invite us to reconsider our relationship with nature and the environment. In a world where everything is interconnected, how do we approach issues such as climate change, resource depletion, and ecological preservation? Perhaps the recognition of our entangled existence can inspire a deeper sense of stewardship towards the planet, encouraging us to act in ways that honor our interconnectedness with all living beings. As we reflect on these themes, we find ourselves standing at the crossroads of science, philosophy, and ethics, where the mysteries of entanglement beckon us to explore uncharted territories. The implications of this phenomenon extend far beyond the confines of the laboratory, inviting us to engage with the very essence of our existence. In this vast landscape of ideas, we are reminded of the importance of dialogue and collaboration. As scientists, philosophers, and thinkers from diverse fields come together to explore the implications of entanglement, we open ourselves to new perspectives and insights. The journey into the philosophical implications of entanglement is not one that can be undertaken in isolation. It is a collective endeavor that invites us to embrace curiosity and wonder. Ultimately, the exploration of entanglement invites us to view the universe through a lens of interconnectedness, where separateness is but an illusion. As we ponder the nature of reality, we begin to see the beauty in the intricate web of existence that binds us all. In this shared journey, we may discover that the quest for understanding is not merely an intellectual pursuit, but a deeply human endeavor, one that speaks to our longing for connection, meaning, and purpose. As we continue to traverse this philosophical landscape, we find ourselves enriched by the questions posed and the insights gained. The implications of entanglement resonate deeply, inviting us to engage with the fundamental mysteries of existence and to celebrate the interconnectedness that defines our journey through life. As we explore the rich philosophical landscape shaped by quantum entanglement, we begin to encounter profound implications for our understanding of time itself. Traditionally, we perceive time as a linear progression, a sequence of events unfolding in a cause and effect manner. Yet, the phenomenon of entanglement hints at a far more intricate relationship with time, suggesting that past, present, and future may not be as distinct as we once believed. Imagine a river flowing, where each drop of water represents a moment in time, yet at certain points, the waters converge, intertwining in ways that defy linearity. Could it be that the entangled nature of particles allows glimpses into a more fluid understanding of temporal existence? In this context, we might ponder how the interconnectedness of entangled particles influences our perceptions of time and causality. If the state of one particle can instantly affect another, regardless of the distance separating them, what does this mean for events that we consider temporally bound? Are we witnessing a reality where the influence of past events reverberates into the present and future, reshaping our understanding of causation itself? As we reflect on these questions, we are reminded of the delicate dance between determinism and free will we previously examined. The discussion surrounding entanglement has also sparked a renaissance in metaphysical thought. Philosophers are now revisiting age-old questions about the nature of being and existence through the lens of quantum mechanics. Is there a fundamental essence that binds all matter and consciousness, transcending the physical boundaries we have constructed? Are our thoughts and emotions merely manifestations of entangled interactions, echoing the patterns found in the universe at large? The interplay between quantum entanglement and consciousness invites us to reimagine our place within the cosmos, suggesting that we may be more than just passive observers. We are active participants in a vast and interconnected reality. Moreover, the implications of entanglement extend into the realm of ethical considerations, where the recognition of our interconnected existence calls for a deeper sense of responsibility. If our lives are woven together through the threads of entanglement, how does this shape our moral obligations to one another and to the environment? Imagine a world where every action is viewed through the prism of its potential impact on the collective. This shift in perspective encourages us to cultivate empathy, compassion, and a sense of stewardship for both our fellow beings and the world we inhabit. As we delve deeper into the philosophical discourse surrounding entanglement, we come across the intriguing concept of non-separability, which posits that the properties of entangled particles cannot be understood independently of one another. This idea challenges the very foundation of individualism that permeates much of our societal structure. In recognizing that the essence of our existence may be inherently linked to others, we are invited to reconsider our definitions of self and other. How might this understanding transform our interactions, fostering a sense of unity amidst diversity? The journey through these philosophical implications continues to illuminate the intricate connections between science, ethics, and our understanding of reality. In this age of rapid technological advancement, the principles gleaned from quantum entanglement offer a framework for navigating the complexities of our modern lives. As we harness the power of quantum innovations, we are also challenged to integrate these insights into our collective consciousness, shaping a future that honors the interconnectedness of all things. In this exploration, the voices of great thinkers resonate, urging us to embrace the uncertainties and complexities that lie ahead. The philosophical implications of entanglement beckon us to engage in continual dialogue, fostering a spirit of inquiry that transcends boundaries. Are we prepared to embark on this journey of exploration, to challenge our preconceived notions and embrace the profound mysteries that quantum mechanics unveils? As we stand at the crossroads of science and philosophy, we find ourselves enriched by the myriad questions posed and the insights gained through our exploration of entanglement. With each question, we peel back the layers of existence, revealing the intricate web of connections that bind us to one another and to the universe itself. The philosophical implications of entanglement not only invite us to ponder our place within the cosmos, but also inspire us to act with intention in the interconnected reality we share. Chapter 9: Future Research Directions in Quantum Entanglement. In the ever-evolving landscape of quantum entanglement, we encounter a tapestry of unresolved questions and uncharted territories. While we have made significant strides in understanding the nature of entanglement, substantial gaps still linger, leaving scientists eager for deeper insights. One of the most pressing gaps lies in the interpretation of entangled states. What precisely happens when entangled particles are measured? The phenomenon of wave function collapse remains shrouded in mystery, creating a divide in interpretations of quantum mechanics. Imagine two entangled particles as dancers in a duet, gracefully intertwined, yet leaving us questioning the true nature of their connection when the music stops. This ambiguity invites us to ponder, could there be underlying mechanisms that govern entanglement beyond our current understanding? The search for clarity is not merely a philosophical endeavor. It has practical implications for developing quantum technologies. A deeper understanding of entanglement could unlock advancements in quantum computing and communication, leading to innovations that we can only begin to envision. As we look to the future, new theories and experimental approaches are emerging, promising to illuminate the shadowy corners of quantum entanglement. One exciting avenue is the exploration of entanglement in higher dimensions. Traditional experiments have largely focused on entangled particles in two-dimensional states, yet the universe is a rich tapestry of dimensions waiting to be explored. Consider the implications of entangled particles existing in 4 or more dimensions. How would the correlations between them manifest? What new phenomena might emerge from such explorations? Physicists are also investigating the role of entanglement in complex systems, such as those found in condensed matter physics. The interplay between entangled particles within solid-state systems could lead to groundbreaking discoveries in materials science. Imagine materials that exhibit unique properties due to their entangled states, transforming the way we approach technology and engineering. Researchers like Juan Maldacena have proposed intriguing theories that intertwine entanglement with aspects of gravity, suggesting that entanglement may play a fundamental role in the fabric of space-time itself. The pursuit of understanding entanglement is not confined to a single discipline or perspective. Interdisciplinary studies are emerging, drawing insights from physics, mathematics, and even philosophy. The boundaries between these fields begin to blur as researchers collaborate to forge new paths in understanding this enigmatic phenomenon. For instance, the application of information theory to quantum entanglement has opened doors to new methodologies and concepts. How might the principles of information flow influence our comprehension of quantum systems. Imagine a world where the insights of computer science merge seamlessly with quantum mechanics, leading to fresh paradigms in how we approach complex problems. This interdisciplinary synergy could yield innovative solutions, blending the abstract with the tangible and reshaping the future of technology. International collaboration plays a vital role in the advancement of research in quantum entanglement. As the scientific community converges across borders, the sharing of knowledge and resources fosters an environment ripe for discovery. Joint experiments and collaborative projects leverage the strengths of diverse teams, amplifying the potential for breakthroughs. Consider the global efforts in quantum key distribution, where researchers from different countries unite to develop secure communication systems. The interconnectedness of our world mirrors the very principles of quantum entanglement itself, as scientists work together, transcending geographical boundaries to unravel the mysteries of the quantum realm. This collaborative spirit is also evident in the establishment of international research facilities and initiatives. Large-scale projects, such as quantum research centers, bring together experts from various disciplines to focus on cutting-edge problems. Within these collaborative frameworks, scientists can share diverse perspectives, fostering creativity and innovation. The results of such partnerships can lead to advancements that would be challenging to achieve in isolation. As we contemplate the future of quantum entanglement research, it becomes clear that the journey ahead is filled with potential. The gaps in our understanding serve not as obstacles, but as invitations to explore the unknown. New theories and experimental approaches beckon us to venture into realms yet uncharted, while interdisciplinary studies promise to enrich our insights and foster collaboration across borders. Imagine a future where the mysteries of entanglement are not merely theoretical discussions, but are woven into the very fabric of our technological advancements. The potential applications are vast, from revolutionizing computing to providing unprecedented security in communication. As we stand on the cusp of this new era, we are reminded of the profound interconnectedness that entanglement embodies, shaping not only our understanding of the universe, but also our collective future. In this journey, we may find ourselves returning to the fundamental questions that have driven humanity's quest for knowledge. What does it mean to be connected? How do our actions resonate across the fabric of reality? These inquiries echo through the corridors of scientific discovery, urging us to delve deeper into the mysteries that quantum entanglement presents. As we continue to unravel its complexities, we are inspired to embrace the unknown, knowing that each step forward may reveal a greater understanding of the universe and our place within it. The horizon of quantum entanglement glows with promise, inviting us to embark on a journey rich with exploration and wonder. Each new theory, experiment, and collaboration is a thread woven into the intricate fabric of scientific progress. As we prepare to delve deeper into this realm, we hold in our hearts the hope that the future may illuminate not only the nature of entanglement, but also the very essence of our interconnected existence. As we journey further into the unfolding story of quantum entanglement, we find ourselves standing at the precipice of discovery, where current gaps in understanding beckon for exploration. The enigmatic nature of entanglement continues to challenge our intellects and imaginations. One particularly intriguing area of inquiry revolves around the scalability of entangled states. How do we transition from small systems where entanglement has been extensively studied to larger, more complex systems that could potentially harness entanglement for practical applications? Imagine a vast web of entangled particles stretching across dimensions, each thread representing a connection that could facilitate communication or computation. The challenge lies in maintaining the delicate balance of entanglement within larger systems, where environmental interactions threaten to disrupt these fragile relationships. Researchers are actively exploring methods to protect entangled states from decoherence, a process where entanglement is lost due to interactions with the environment. Could strategies from error correction in quantum computing provide insights into preserving entangled states in more extensive systems? New theories are emerging that propose novel frameworks for understanding entanglement. One such approach is the study of entanglement dynamics, how entangled states evolve over time and how they can be manipulated. This inquiry invites us to consider questions such as, can we control the entanglement of particles to enhance their utility in quantum technology? What strategies might allow us to harness entanglement for specific purposes, like improving quantum communication protocols or optimizing quantum algorithms? Pioneering physicists, including those like David Deutsch, are laying the groundwork for new theories that intertwine quantum mechanics with classical concepts. Deutsch's insights into quantum computation suggest that entanglement could be harnessed to perform tasks that are currently deemed impossible on classical computers. Imagine a world where complex computational problems are solved in mere moments, all thanks to the power of entanglement. As we explore the future landscape of quantum entanglement, we cannot overlook the burgeoning field of interdisciplinary studies. The blending of quantum physics with disciplines such as biology and computer science is paving the way for innovative approaches to entanglement research. Consider the intersection of quantum biology, where researchers are investigating the role of quantum effects in processes like photosynthesis. Could entangled states be integral to the efficiency of energy transfer in biological systems? The prospect of discovering new mechanisms that underpin life itself through the lens of quantum mechanics opens a captivating dialogue between science and philosophy. Moreover, the potential applications of entanglement in information theory extend beyond mere computational advancements. As quantum entanglement intertwines with concepts of information flow, we find ourselves pondering the very nature of knowledge and communication. How might entangled states redefine our understanding of information security? The advent of quantum networks, fueled by entangled particles, aims to create communication systems that are inherently secure, offering a profound shift in how we share and protect information. The role of international collaboration in this exploration cannot be overstated. It is this global effort that brings together brilliant minds from various fields, fostering an environment where ideas can flourish. Imagine laboratories across continents working in tandem, sharing insights and resources to tackle the intricate puzzles of quantum entanglement. The establishment of international consortia and research initiatives has catalyzed a surge in creativity and innovation. As researchers join forces, they often bring diverse perspectives that enrich the collective understanding of quantum mechanics. This collaborative spirit echoes the very principles of entanglement. Particles that are entangled are, in essence, interconnected, regardless of the distance that separates them. The implications of this interconnectedness extend beyond scientific pursuits, reminding us of the shared responsibility we hold in advancing knowledge for the betterment of humanity. The future of quantum entanglement research holds infinite possibilities, from the quest for unifying theories that bridge gaps in our understanding to the practical applications that could arise from such insights. Imagine a world where harnessing the power of entanglement allows us to create energy-efficient technologies or develop revolutionary medical imaging techniques. The path ahead is not merely a scientific endeavor, but a profound journey into the very essence of existence. As we continue to traverse this landscape, we are reminded of the elegance that lies within the mysteries of quantum entanglement. Each new discovery, each collaborative effort, serves as a stepping stone toward a deeper comprehension of the universe. The questions we encounter along the way are not mere hurdles, but invitations to explore the unknown, to embrace the complexities that make our quest for knowledge so rewarding. In pondering the future of quantum entanglement, we find ourselves inspired by the potential for breakthroughs that could transform our understanding of reality. The pursuit of knowledge in this field is a testament to the resilience of human curiosity, a journey that transcends boundaries and unites us in the shared wonder of the cosmos. As we look ahead, we can only imagine the rich tapestry of discoveries that await, urging us to venture forth with open minds and hearts. As we delve further into the future of quantum entanglement research, the notion of scalability emerges as a fundamental challenge. The leap from small-scale entangled systems to larger, more complex configurations presents both technical hurdles and exciting possibilities. Imagine a network of entangled particles, forming a vast interconnected web, each point representing a potential for instantaneous communication or computation. Yet maintaining entanglement across a larger array of particles is a delicate endeavor, often threatened by environmental interactions that induce decoherence. Researchers are now exploring novel techniques, such as topological qubits, which may provide robustness against such disturbances. Could these advancements allow us to harness entanglement in practical, large-scale applications? The exploration of entanglement dynamics also invites us to consider how entangled states evolve and can be manipulated. This line of inquiry opens doors to innovative ways to utilize entanglement in quantum technologies. For instance, could we develop methods to reliably generate and maintain entangled states on demand, paving the way for more efficient quantum algorithms? The potential for entanglement to enhance quantum information processing is immense, leading us to ponder what discoveries might lie ahead. In the realm of interdisciplinary studies, the intersection of quantum physics with fields like neuroscience is becoming increasingly intriguing. Researchers are beginning to investigate whether quantum effects might play a role in cognitive processes. Imagine if entangled states could contribute to the workings of the human brain, influencing how we process information or make decisions. This blending of disciplines not only enriches our understanding of entanglement, but also prompts us to question the very nature of consciousness itself. The global landscape of quantum research benefits immensely from the spirit of collaboration. As scientists from diverse backgrounds unite, their collective expertise fosters an environment ripe for discovery. Joint initiatives, such as those seen in international quantum technology conferences, encourage the exchange of ideas and methodologies, breaking down barriers that once limited progress. Could the synergy of these global partnerships lead to breakthroughs that forever alter our understanding of quantum entanglement? The drive for innovation in quantum communication systems is another area where international collaboration shines. Researchers are working together to develop quantum networks that promise to revolutionize secure communication. Picture a world where messages are transmitted with unbreakable encryption, harnessing the principles of entanglement to ensure privacy. This collective effort underscores the importance of sharing knowledge and resources as countries come together to create a secure quantum internet. As we stand at the brink of new discoveries in quantum entanglement, it is essential to reflect on the philosophical implications that accompany these advancements. The interconnectedness witnessed in entangled particles serves as a reminder of the intricate web of relationships that bind our universe. Our pursuit of knowledge in this field may ultimately lead us to reevaluate our understanding of reality, challenging the very foundations upon which we build our beliefs about separation and individuality. The exploration of entanglement is not merely a scientific endeavor. It is a profound journey that intertwines the fabric of our existence with the mysteries of the universe. Each question we encounter invites us to deepen our exploration, to embrace the unknown, and to revel in the beauty of discovery. As we continue to unravel the complexities of quantum entanglement, we are not only expanding our scientific horizons, but also illuminating the pathways to a future rich with potential and wonder. Chapter 10: Quantum Entanglement and the Universe. As we conclude our journey through the universe of quantum mechanics, we arrive at a phenomenon that invites us to reconsider our understanding of reality itself: quantum entanglement. This intricate web of connections between particles not only challenges our classical intuitions, but also beckons us to explore its implications within the vast cosmos. The relationship between entanglement and cosmology is a captivating subject, as it hints at a reality that transcends our conventional notions of space and time. Imagine a universe where the separation between distant galaxies is bridged by an invisible bond, where the states of particles can influence one another across unimaginable distances. This is the essence of entanglement. It suggests that the universe may be more interconnected than we perceive, weaving a fabric that defies the linear progression of time and space. The implications of this interconnectedness ripple through the fabric of space-time itself, suggesting that events occurring at one point in the universe can have instantaneous effects elsewhere. What if we expand this idea? Could entangled particles act as messengers, carrying information across the cosmos in ways that challenge our understanding of causality? In this view, entanglement becomes a crucial element in the broader tapestry of cosmology, hinting at a universe where connectivity is intrinsic. It raises questions about the origins of the universe itself. Did entanglement play a role in the moments after the Big Bang, creating a web of connections that shaped the evolution of matter and energy? As we ponder these questions, we uncover the role of entanglement in theories of quantum gravity. These theories strive to unify the principles of quantum mechanics with those of general relativity, our best description of gravity. Picture a universe where the very fabric of space-time is molded by entangled particles, where gravity and quantum mechanics coexist in a harmonious relationship. This is no small feat, as reconciling these two pillars of physics has long eluded scientists. One prominent theory, loop quantum gravity, suggests that space-time itself may be quantized, made up of discrete units, rather than being a smooth continuum. Here, entanglement emerges as a critical player, as relationships between these discrete units could define the structure of space-time. Imagine a vast cosmic quilt, each patch representing a piece of space-time, stitched together by the delicate threads of entanglement. This perspective opens up fascinating avenues for understanding the universe's structure, leading us to consider how entangled states might influence the fabric of reality at its most fundamental level. As we delve further into the implications of entanglement, the future explorations promise to be even more intriguing. Scientists are now investigating how entanglement can help us decipher the mysteries of the universe, from the behavior of black holes to the dynamics of cosmic expansion. What secrets might be hidden within these entangled states? Could they offer insights into dark matter and dark energy, those elusive components that seem to govern the universe's expansion? Consider the possibility of entangled particles serving as probes for exploring the cosmos. As they interact with gravitational fields, do they retain their entangled state? Investigating these questions could lead us to novel experimental techniques, paving the way for a deeper understanding of the universe's workings. This exploration will not only enhance our grasp of theoretical physics, but could also yield practical applications in quantum communication and computation. The ongoing research into entanglement is not merely an academic endeavor. It is a quest that intertwines with our fundamental desire to comprehend our place in the universe. Each discovery invites us to look deeper, to challenge our assumptions, and to embrace the wonders of the unknown. Prominent physicists such as John Wheeler have famously said, "We are not just passive observers of the universe, we are participants in its unfolding." This sentiment captures the essence of our journey through quantum entanglement and cosmology. As we participate in this exploration, we become part of a narrative that transcends time and space, revealing the profound interconnectedness of all things. As we envision the future of entanglement research, we are reminded of its potential to reshape our understanding of reality. Each experiment, each theoretical breakthrough, serves as a stepping stone into the vast unknown. The universe, with its mysteries and marvels, beckons us forward, inviting us to explore the depths of entanglement and its implications for the cosmos. What might we uncover in the coming years? Could entanglement lead to a deeper understanding of consciousness, or help us bridge the gap between mind and matter? The possibilities are as limitless as the universe itself, each thread of inquiry weaving into the grand tapestry of existence. As we reflect on our journey, we carry with us the insights gained from exploring quantum entanglement and its relationship to the universe. This exploration has illuminated the intricate connections that bind us to the cosmos, revealing a reality both enchanting and perplexing. The path ahead is filled with promise, a testament to humanity's unyielding curiosity and the enduring quest for knowledge. As we stand at the precipice of discovery, we embrace the mysteries that lie ahead, ready to engage with the wonders of quantum entanglement and the universe. The journey continues, inviting us to ponder the profound questions that shape our understanding of existence. What revelations await us in this grand exploration? The answers may be hidden within the very fabric of the cosmos, waiting to be unveiled as we venture forth into the unknown. As we consider the implications of entanglement in cosmology and the fabric of space-time, it becomes evident that this phenomenon not only enriches our understanding of the universe, but also reshapes our approach to fundamental physics. Imagine a cosmos where the intricate relationships between particles are mirrored in the grand design of galaxies and cosmic structures. This interconnectedness hints at an underlying principle that binds the cosmos together, transcending the boundaries of space and time. The implications for the fabric of space-time are profound. Traditional views of space-time, as described by Einstein's theory of general relativity, depict it as a smooth, continuous entity, influenced by mass and energy. However, when we introduce the concept of quantum entanglement, the picture becomes more complex. Picture space-time not as a static backdrop, but as a dynamic, responsive entity, shaped by the entangled states of particles. This perspective invites us to explore how entangled particles might interact with gravitational fields, potentially revealing new insights into the nature of gravity itself. Consider the possibility that entanglement could provide a bridge between quantum mechanics and general relativity, two pillars of modern physics that have traditionally remained at odds. The work of theoretical physicists like Carlo Rovelli and Lee Smolin has opened new avenues in this quest. They propose that space-time may emerge from the interactions and entanglements of quantum states, suggesting a revolutionary approach to understanding the universe's structure. What if space-time itself is a manifestation of these entangled relationships, a tapestry woven from the threads of quantum connections? As we delve deeper into the relationship between entanglement and quantum gravity theories, we can envision a universe where the geometry of space-time is not merely a passive entity, but an active participant in the unfolding drama of cosmic events. This perspective aligns with the principles of loop quantum gravity, where space-time is quantized into discrete units. In this framework, entanglement could serve as the glue that holds these units together, much like the connections between neighborhoods in a sprawling city. Each neighborhood represents a segment of space-time, and the entangled relationships between them dictate the movement and evolution of the entire structure. Furthermore, the exploration of entanglement opens up new questions about the nature of black holes. These enigmatic entities, with their immense gravitational pull, challenge our understanding of physics. As we ponder the role of entanglement in black hole dynamics, we might ask, do entangled particles near the event horizon behave differently than those further away? The concept of black hole complementarity suggests that the information about particles entering a black hole may be preserved, encoded in the entangled states of particles outside its grasp. This raises profound implications for our understanding of information and the ultimate fate of matter in the universe. Future explorations into quantum entanglement may also lead us to rethink our understanding of cosmic expansion. The universe has been expanding since the Big Bang, a phenomenon driven by mysterious forces that remain poorly understood. Could entangled particles provide insights into this expansion? Imagine a scenario where entangled states can reveal the interactions between dark matter and dark energy, those elusive components that dominate the universe's dynamics. By studying the behavior of entangled particles in various cosmic environments, scientists may be able to uncover the secrets behind these enigmatic forces. As we peer into the horizon of entanglement research, we encounter a tapestry of possibilities. The future holds immense potential, not only for theoretical advancements, but also for practical applications that could reshape our technological landscape. Quantum computing, for example, relies heavily on entanglement to achieve unprecedented computational speeds. As researchers continue to push the boundaries of this technology, we may discover new ways to harness the power of entangled states for solving complex problems in fields ranging from cryptography to drug discovery. The journey of exploring quantum entanglement is not solely a scientific endeavor. It resonates with humanity's intrinsic curiosity and desire for understanding. Each new discovery serves as a reminder that we are participants in the cosmic narrative, engaged in a constant quest for knowledge. What mysteries lie ahead, waiting to be unveiled? As physicists and cosmologists delve deeper into the realm of entanglement, they may uncover not only the fundamental workings of the universe, but also insights into our place within it. In this grand exploration, we come to appreciate that quantum entanglement is more than a curious scientific phenomenon. It is a lens through which we can view the universe in all its complexity and interconnectedness. The questions it raises are as profound as the answers it seeks. As we stand on the brink of these discoveries, we are reminded that the universe is a vast and vibrant stage, inviting us to explore its hidden depths. What connections might we uncover between entangled particles and the very essence of existence? The answers await us, hidden in the intricate weave of the cosmos, calling us to continue our journey of exploration and understanding. The exploration of quantum entanglement opens up a realm of possibilities that extend far beyond our current understanding of physics. As we consider its implications for the fabric of space-time, we begin to grasp the transformative potential of this phenomenon. What if entanglement serves as the connective tissue of the universe, binding particles and galaxies into a seamless whole? Such a perspective invites us to rethink our assumptions about both the microcosm of particles and the macrocosm of the cosmos. In the context of cosmology, entanglement may provide a framework for understanding the origins of cosmic structures. Picture the early universe, a hot, dense state teeming with energy. In those nascent moments following the Big Bang, could entangled particles have been the catalysts for the formation of galaxies and clusters? This line of inquiry opens doors to investigating how entanglement might influence cosmic inflation, an exponential expansion that shaped the universe we perceive today. Researchers are actively probing these connections, seeking to unravel the mysteries of how entanglement could influence the distribution of matter across vast distances. As we journey deeper into the implications of entanglement, the role it plays in quantum gravity theories comes to the forefront. The quest to unify quantum mechanics and general relativity has long been a holy grail for physicists. What if the secrets to this unification lie within the tangled relationships of entangled particles? The notion that space itself might be emergent, arising from quantum entanglement, reshapes our understanding of reality. It suggests a universe where distances are not merely measured in light years, but are instead informed by the intricate relationships between quantum states. Consider the profound implications of this idea. If space-time is woven from entangled particles, then the very act of observing one particle could influence the structure of the cosmos itself. This perspective aligns with the notion of non-locality, where events at one point in space can instantaneously affect distant events. Such a concept challenges the traditional view of causality and invites us to rethink the nature of time. Could time be an emergent property, a byproduct of entangled interactions, rather than a linear progression? Future explorations of entanglement promise to deepen our understanding of these intricate relationships. As scientists develop new experimental techniques to probe the entangled state of particles, they may uncover insights that challenge our very understanding of the universe. Imagine a future where quantum experiments conducted in space reveal new connections between entanglement and the behavior of cosmic phenomena, such as black holes or neutron stars. This research could lead to breakthroughs in our understanding of dark matter and dark energy, those elusive components that constitute much of the universe's mass energy content. The tantalizing prospect of entangled particles serving as cosmic messengers inspires a sense of wonder. What if they could convey information about the state of the universe itself? This idea aligns with ongoing discussions regarding the potential for quantum communication systems to operate over astronomical distances, leveraging the power of entanglement to transmit information instantaneously across the cosmos. This could revolutionize our approach to understanding not just the universe, but also our relationship with it. As we reflect on the myriad possibilities entangled with the future of quantum research, we are reminded of the words of physicist Richard Feynman, who said, "The imagination of nature is far greater than the imagination of man." This sentiment resonates deeply as we embark on this journey, where the unknown beckons us to explore further, to question, and to discover. Ultimately, the future of quantum entanglement is not merely a scientific endeavor. It is an invitation to engage with the mysteries of existence itself. Each new revelation opens a window to a universe that is both familiar and profoundly alien. As we stand on the cusp of discovery, we carry with us the knowledge that every question leads to new questions, and every exploration unravels yet another thread in the vast tapestry of the cosmos. What awaits us in this grand adventure? The answers lie hidden within the intricate dance of quantum entanglement, waiting to be revealed as we continue our quest for understanding.